Rotational inertia is a quantity that we'll use quite a bit with rotational motion. And kind of the definition of rotational inertia is that it's the rotational equivalent of mass. Now, that may seem a little bit strange because most of our other rotational quantities are kind of the rotational equivalent of something that's a vector, like rotational velocity, rotational acceleration, or even torque is kind of the rotational version of force. And clearly mass is not a vector. So to understand why we have a rotational equivalent of mass, it's important to think about the meaning of mass in physics. In physics, we say that mass is how much inertia something has, or its resistance to a change in its motion. So when you think about it that way, the resistance to a change in its motion, it makes a little bit more sense that we have a rotational equivalent to mass. Rotational inertia would be how much an object resists a change in its rotational motion. And it depends not only on our object's mass, but also on its shape and size and where the axis of rotation is located. If we have a particle or something that we can treat like a particle, that equation for the moment of inertia is mr squared. I represents that moment of inertia, and it has units, kilogram meter squared. When we say that we use this for a particle, it can be anything that is also particle-like. So for example, when the Earth is rotating around the sun, we would consider the Earth to be a particle because its size is small compared to the distance between the Earth and the sun. If we have multiple particles, then the moment of inertia of our system would be the sum of m times r squared for each particle, where again m is the mass and r is the distance from that particle to the axis of rotation. Now, as we've done in past units in this course, if we want to go from having multiple objects to having a solid particle, often we turn that summation sign into an integral sign. And in this case, instead of doing m times r squared, we're doing r squared times dm. So we're taking a little piece of mass that we can basically treat like a particle, and we are multiplying it by how far that little piece of mass is from the axis of rotation. Now, just like we've seen before when we did center of mass calculations, we will substitute in for dm according to what our object is like. So if we have something that's one-dimensional, then we say that it has a linear mass distribution lambda, and typically we'll do lambda times dx or dy or dz depending on where, kind of what axis your object is on. If we have something two-dimensional, then we'll use that surface mass distribution times a little bit of area. And if we have something that is three-dimensional, we'll use that volume mass distribution rho times a little bit of volume. And so we'll see some practice in using that. And that's actually our next step. One of the things that the AP College Board requires you to know how to do is to derive the expression for the moment of inertia of a uniform rigid rod. And so that's what we're going to do here with that axis of rotation located at the center of our rod. The problem gives us two variables, m for the mass of the rod and L for the length of the rod. And so those are the variables that should be in our final expression. So in order to do this, we are going to start by choosing a small piece of mass, the little piece of mass dm. I'm going to say that that little piece of mass dm has a length of dx, and that the center of that little piece of mass is located a distance x from my axis of rotation. So we always want to start with something that's on the equation sheet. And that equation I equals r squared dm is on your equation sheet. Since we have something that is one-dimensional, we'll use that linear mass distribution here. And by the fact that it says that it's a uniform rigid rod, that word uniform indicates that lambda is constant. So mass is uniformly distributed throughout the rod. And so subbing that in for dm, instead of using r in this case, I'm going to use x squared, since I defined x to be my quantity from where the little piece of mass was located to the axis of rotation. And then I'll sub in lambda dx. Now I also want to put limits on this integral. So I want to think about what is the biggest and smallest x can be. So in other words, what if I choose a piece of mass that's all the way at the left end here? Well, that would be located a distance of negative L over 2 from my axis of rotation. Negative since it's to the left of the axis of rotation, of course. Similarly, if I choose a piece of mass that's all the way at the right end, that right end is located a positive L over 2 from my axis of rotation. My limits on this expression are going from negative L over 2 to positive L over 2. To evaluate this integral, I can pull lambda out because it's a constant. And then I have the integral of x squared dx, which is a relatively straightforward integral to take. You get x cubed over 3. And then we have to evaluate between our limits. So when we are evaluating that from our limits, I want to make sure that I am cubing both the L and the 2. So 2 cubed is 8. When I cube that negative L, I get negative L cubed. And then I can simplify this expression. Of course, it's always a bad idea to leave fractions within fractions. And so when I simplify this, I end up getting 1/12 lambda L cubed. Now, we said that our final expression had to have L and M in it. Lambda was not something we were allowed to keep in there. So we'll need to sub in for lambda. Because lambda is constant, I can also say that the total mass is equal to lambda times the total length. So when I'm subbing in, I can say that instead of lambda, I have m over L. And that then simplifies to being the moment of inertia is equal to 1/12 ml squared. And if you look that up in a textbook, you'll find this moment of inertia in a chart that gives you moment of inertias of various common objects. So we're going to do the same process again. So for our second example here, we have a solid cylinder. It is a uniform cylinder with a length of L, radius R, and mass M, and our axis of rotation passes through the center of the cylinder. And it might not look perfectly like that on the diagram that you see here. We'll have to use our imagination, since drawing a three-dimensional object on a two-dimensional space is challenging. I'm going to go ahead and mark in that length, that radius, just so we remember what that's talking about here. And we'll want to make sure that L, R, and M are the only things in our final expression. So we will start with the moment of inertia equation. Moment of inertia is the integral of r squared dm. And this time we have a three-dimensional shape. So our little bit of mass is going to be equal to volume mass density times a little bit of volume. Let's go ahead and define that little bit of mass right now. Last time that little bit of mass was kind of like a point particle. This time my little bit of mass is actually going to be a kind of hollow cylinder itself. And the reason I'm using a hollow cylinder for that little bit of mass is every point on that cylinder is going to be the same distance away, the same R value from my axis of rotation. So it kind of just simplifies things a little bit. My cylinder has a little bit of mass, is going to have a thickness of dr. It's going to have a circumference kind of around the top of 2 pi times little r. And it's going to have a length of L, just like the original cylinder. So my volume, my little bit of volume in this case, is going to be equal to that circumference, 2 pi little r, times the length of my cylinder, times that little bit of thickness, because again, it can't have 0 thickness, it has to have a little bit. So you could almost think of it as if we were looking top down, it would have just a tiny bit of thickness, and that distance between those two circles would be my dr here. So I'm going to use that in my expression here. I have the integral of r squared times rho times 2 pi r L dr in this case. The smallest my radius of my cylinder could be is 0. The largest my radius could be is capital R. So those are my limits on my integral. To make it easier to take the integral, I'm going to pull out my constants, and there's quite a few of them here. 2 pi, rho is a constant because it's a uniform mass distribution, and L is a constant. And so then I'm left with the integral from 0 to capital R of r cubed dr. And that's a fairly easy integral to take once again here. It gives us r to the 4th over 4. We evaluate between 0 and capital R. So we end up with 2 pi rho L times capital R to the 4th divided by 4. And of course we can simplify that 2 goes away and this 4 becomes a 2. So I could say 1/2 pi rho L r to the 4th. Now of course I'm not allowed to have rho in there. And so similar to what we did in that last problem, we're going to also say, since it's a uniform mass distribution, that the total mass is equal to rho times the total volume. And I have to be honest, I don't have those things memorized, the volume of a solid cylinder. So instead I've reasoned my way through it. When I'm thinking about volume, I'm thinking about the area of one of the surfaces, and then I multiply that area times the dimension that's not included. So I could think the area of the top circle of my cylinder, and I know the area of a circle, that's one I do have memorized. That's pi r squared, and then don't have that length included. So I think of pi r squared times the length, and that gives me the volume of my cylinder. So that means that if I solve this equation for rho, I get that rho is equal to mass divided by pi r squared L. So I'm going to plug that in for my expression for moment of inertia. So I have 1/2 pi L r to the 4th times that mass divided by pi r squared L. So you'll see that the pi's cancel out. This r squared cancels out here with 2 of those, and the L's cancel out as well. I'm left with the final expression of I equals 1/2 mr squared for a solid cylinder with the axis of rotation passing through its center. Now, pretty much any physics textbook is actually going to include a table of moment of inertias, like you see here. This is not the one that's in your textbook, but it's one that's similar to what you have. And so in this table, you can see those 2 equations that we derived. That equation for a long thin rod about its center, 1/12 ml squared, as well as a solid cylinder. It also works for a disk, which is just something that doesn't have a very long length. We get that 1/2 mr squared. You need to be able to derive those 2 expressions, which means anytime that you have to use those expressions in a physics problem, you should derive them based on what's on the equation sheet until you get really comfortable with those derivations. However, if a problem includes a different shape, so for example, let's say that we have a problem where something in the problem is a solid sphere, like what we see here. That is really challenging to derive an expression for, so instead you are welcome to look up the expression and just use it as is. So you'll see this one is 2/5 mr squared. There is one other you should be able to derive, and that's this thin rod about one end. So this one all the way on the bottom left down here. And so we're going to talk about how to do that. There's two ways to derive that expression. One way would be very similar to what we did for the thin rod about its center. The only difference here would be the limits that you would use. But there's another way that I think is a bit easier, and that's using something called the parallel axis theorem. So this parallel axis theorem is commonly used when your axis of rotation does not pass through the center of mass. And it's a actually relatively simple way of finding the moment of inertia for your object. This is an equation that is not on the equation sheet, but because it's so useful, it's one of the few equations that I suggest that you memorize. The equation says that the moment of inertia is equal to the moment of inertia sorry, let me rephrase that. This right here is your moment of inertia for when your axis of rotation passes through the center of mass, plus the object's mass times the distance from the center of mass to the new axis of rotation squared. That's kind of a mouthful. So here's an example of that. Using those long thin rods on that previous slide, let's say that we started out with 1/12 ml squared. That's what we derived when the axis of rotation is about its center, plus mass times the distance from the center of mass to where the axis of rotation is. So if the axis of rotation is at one end, that distance is L over 2 squared. So I can simplify that, 1/12 ml squared plus 1/4 ml squared. I can simplify that even further to get 1/3 ml squared, which is what we saw on that equation sheet there. So you can go through that whole derivation and switch the units, or you could use this parallel axis theorem to make your life a little bit easier if you choose.